February 15, 1944, Ladd Field, just outside Fairbanks, Alaska. The thermometer outside Hangar 1 reads 48 degrees below 0 Fahrenheit. A mechanic named Sergeant Walter Anderson is standing on a wooden trestle next to the number 3 engine of a B-24E Liberator, tail number 427331, stenciled Yellow 31 on the fuselage. He has been at this engine for 53 minutes. He has not been able to turn the propeller by hand even 1 degree. The reason is not the engine. The engine is a Pratt & Whitney R1830 Twin Wasp, a 14-cylinder radial that, by all engineering measurements, should start in any temperature down to about -30 if the oil dilution system has been used properly. The crew chief had diluted the oil the previous evening. The cylinders are dry. The fuel is good. The battery cart is hooked up. The problem is the wheel bearings. The problem is the bearings in the supercharger drive. The problem is the bearings in the magneto and the generator and the starter motor itself. The grease packed into those bearings, every one of them, is no longer a lubricant. It is a hard yellow wax. The temperature has driven the calcium soap thickener used in the standard military grease past its operational limit, past its useful limit, into a state where the grease has separated, hardened, and frozen solid against the surfaces it was meant to protect. Anderson eventually starts the engine. It takes him another 40 minutes, 2 propane heaters, and a section of canvas tarp draped over the entire engine nacelle to warm the bearings enough to allow rotation. The aircraft will fly that day. It will fly because Anderson is a good mechanic and because Ladd Field, by 1944, has worked out the ground procedures necessary to operate American aircraft in conditions the designers never anticipated when they built them. But Anderson knows, and every other mechanic at Ladd Field knows, that the airplane is not really designed for this. The lubricants are not really designed for this. And somewhere in a laboratory in the United States, a chemist has been working for 2 years on a solution, a new kind of grease, a new chemistry, a thickener that does not turn solid at 40 below. The chemist's name is Clarence Earl. He has just filed a patent. The patent number is 2274675. It will, in the years that follow, change every Allied bomber that flies an Arctic mission, and almost nobody in the United States Army Air Forces in 1944 has any idea who he is.
To understand the bearing grease problem, it helps to know what grease actually is. Most people assume grease and oil are different substances. They are not. Grease is oil. Grease is a base oil suspended inside a thickening agent, the way water is suspended inside a sponge. Squeeze the sponge and water comes out. Apply pressure or friction to grease, and the base oil seeps out of the thickener, lubricating the moving part. The thickener is a reservoir. The base oil is the actual lubricant. What makes grease useful is exactly this property of staying where it is put. An aircraft engine cannot recirculate oil to every bearing on the airframe. The wheel bearings on the landing gear are out in the open. The bearings in the propeller pitch control mechanism are inside the propeller hub. The bearings in the starter motor, the generator, the magnetos, the supercharger drive, the various pulleys and hinges and pivots and slides on the airframe, all of these are surfaces that move against each other. All of these need lubrication, and none of them can be connected to the engine's pressurized oil system. They need a lubricant that will stay put. They need grease. The first modern greases were calcium-based, dating back to 1845. They were made by combining lime, animal fat, and mineral oil to produce a stable semi-solid lubricant. By the 1920s and 1930s, sodium-based greases had been developed for higher temperature applications. Aluminum and barium soaps followed. Each thickener had its own properties. Calcium greases were water-resistant but limited in temperature range. Sodium greases tolerated heat but washed out in wet conditions. None of them performed well in extreme cold. The problem at -40 degrees, the problem Sergeant Anderson encountered with the propeller of that B-24 at Ladd Field, was specific and chemical. The calcium soap thickener in standard military grease at very low temperatures lost its colloidal structure. The oil and the thickener no longer behaved as a unified semi-solid lubricant. The grease became, in the engineering literature of the period, channeled, meaning the bearing balls cut paths through the hardened thickener but no longer received continuous lubrication. The metal-to-metal contact that resulted, even briefly, was enough to gall a bearing race and condemn the entire assembly. The men who flew bombers in the Aleutian campaign and across the Alaska-Siberia ferry route would discover the consequences of bad grease the same way pilots discovered the consequences of bad oil. By losing engines, by losing aircraft, by losing crews to mechanical failures that should never have happened. The Aleutian Islands campaign began on June 6, 1942, when Japanese forces occupied Attu and Kiska Islands as part of a broader operation tied to the Midway Battle. For 13 months, the United States fought the only land campaign of the Pacific War conducted on North American soil. The fighting itself, on Attu in May 1943 and on Kiska in August of the same year, was brutal, brief, and largely forgotten by American popular memory. What was not forgotten by the men who flew there was the weather. The Aleutian chain produces some of the worst flying weather on Earth. Fog so thick that aircraft taking off from Adak in September 1942 could not see the end of the steel mat runway. Williwaws, the violent katabatic winds that descend from Aleutian mountainsides at velocities exceeding 100 miles an hour. Persistent low ceilings, freezing rain, snow squalls, and ambient temperatures that could drop below 0 Fahrenheit even at sea level in midwinter. At altitude, conditions were worse. The 11th Air Force, the formation responsible for prosecuting the air war in the Aleutians, flew its missions with a mixed force of B-17 Flying Fortresses, B-24 Liberator bombers, B-25 Mitchell mediums, and P-40 Warhawk and later P-38 Lightning fighters. By mid-September 1942, with the runway at Adak finished in just 2 weeks of inventive engineering, B-24 heavy bombers began launching strikes from forward bases against Japanese positions on Kiska. By 1943, more than 100,000 American troops were stationed in Alaska, supported by 13 newly constructed air bases. The maintenance reports from those bases tell a quiet, repetitive story. Bearings froze. Wheel bearings on the landing gear stiffened so severely that aircraft taxiing on hard stands could shear the bolts holding the gear assemblies. Control cables seized in their pulleys. Magneto bearings hardened to the point that engines could not be started without 4 to 6 hours of preheat under canvas covers with propane burners directed at the engine nacelles. The aircraft were not failing in flight. They were failing on the ground before they could ever take off, because the lubricants packed into hundreds of small bearing assemblies could not handle the cold. The American answer to this in 1942 and into 1943 was procedural. Preheat the aircraft, drain the engine oil and warm it on a stove, carry the warm oil back to the aircraft in 5-gallon cans, cover everything in canvas, use propane and electric heaters, send mechanics out in 40 below temperatures to do work that frostbit their fingers within minutes. It worked, after a fashion. It also cost an enormous amount of time, fuel, and manpower for every single sortie launched. What was needed was a chemical solution, grease that simply did not freeze. Clarence Earl was an American chemical engineer working in the petroleum industry in the late 1930s and early 1940s. The biographical record on him is thin. He was not a famous man. He did not win prizes or write books. He did not give speeches. He simply filed patents. Between 1942 and the mid-1940s, he filed at least 5 separate patents on a new type of lubricating grease, the most important of which was United States Patent number 2,274,675, granted on March 3, 1942. The patent was titled Lubricant Containing Lithium Salts. It was the first description in the patent literature of a grease based on lithium soaps. It would, within a decade, change the lubricating grease industry permanently. Today, more than 80 years after Earl's patent issued, approximately 70% of all grease sold worldwide is still based on either simple lithium soap or lithium complex thickener technology.
all of it tracing back to the work Earl did during the early years of the Second World War. What Earl had discovered was deceptively simple. He had found that lithium soaps, the metallic salts formed when lithium hydroxide reacted with fatty acids like stearic, oleic, and palmitic acids, produced a grease with properties that no previous thickener had been able to combine. The lithium grease had a high dropping point, meaning it could tolerate temperatures up to about 350 degrees Fahrenheit without breaking down. It resisted washout by water. It had excellent mechanical stability, meaning it did not break down under shear in heavily loaded bearings, and critically for the application that mattered most in 1942, it remained pliable at extreme low temperatures. The dropping point of a calcium-based grease was around 180 degrees Fahrenheit. The dropping point of a lithium grease was nearly twice that. More importantly, the cold flow characteristics of lithium grease were dramatically better than anything that had come before. A lithium-based bearing grease could be expected to remain lubricating at -40 degrees Fahrenheit, the temperature that had defeated Sergeant Anderson's propeller at Ladd Field, and still function reliably at temperatures up to nearly the boiling point of water. It was, in chemical terms, what the lubricants industry had been trying to achieve for 40 years. It was, in operational terms, the missing piece for American bomber operations in the Arctic. The path from Earl's 1942 patent to operational use on Arctic bomber missions ran through a series of corporate and military steps that almost nobody documented in the popular histories. The patent itself was assigned to the company Earl worked for. The lithium grease formulations were developed for commercial production by several petroleum companies in parallel, including the major suppliers to the United States military: Standard Oil of New Jersey, Texaco, Mobil, Shell, and Sun Oil. The first lithium greases were not labeled with consumer brand names. They were labeled with military specification numbers. The most important wartime specification, the predecessor of today's MIL PRF 23827, established performance requirements for a low-temperature aircraft grease that could maintain its lubricating properties from -65 degrees Fahrenheit to +300 degrees Fahrenheit. No previous grease had ever been required to meet such a range. The lithium formulations did. Production scaled up slowly through 1943 and into 1944. The grease moved from the laboratory benches at the major oil company research centers to pilot production runs of a few thousand pounds to full industrial production runs measured in millions of pounds. The cans, typically 1-pound and 5-pound steel containers stenciled with the military specification number and the manufacturer's lot code, moved by rail to military depots and from there to airfields across the United States, the United Kingdom, North Africa, Italy, the South Pacific, and most importantly for this story, to the airfields of the Alaska-Siberia route and the Aleutian chain. The mechanics who received the new grease were not told that they were handling a revolutionary new product based on a 1942 chemical patent. They were told, in the language of military instruction, that the new grease was the approved lubricant for low-temperature applications and that it was to be used in place of previous grease types in all bearings exposed to extreme cold. The grease guns were filled, the bearings were repacked, the aircraft flew. Performance differences were noticeable almost immediately. Bearings that had previously required 4 to 6 hours of preheat before they would turn could be cranked with the new grease within 10 or 15 minutes of starting cold soak procedures. Generator and magneto bearings that had failed regularly in the winter of 1942-43 stopped failing in the winter of 1944-45. The maintenance burden on Arctic operations dropped sharply. The aircraft availability rate at Ladd Field, at Elmendorf, at Adak, at Shemya, and at the forward fields of the Aleutian chain climbed across the spring and summer of 1944. The men who flew the missions noticed something different. They noticed that the aircraft increasingly simply worked.
The story of how the new grease was validated for combat use runs through Ladd Field, a remote airbase just outside Fairbanks, Alaska,
Established in September 1940 specifically as the United States Army Air Corps' cold weather testing facility. Ladd Field's first commanding officer, Colonel Dale V. Gaffney, who would later become a brigadier general commanding the Air Transport Command's Alaskan wing, had been given the unenviable task of figuring out how to operate American aircraft in the worst winter conditions the continent could produce. The cold weather test detachment that Gaffney led at Ladd Field was, by any measure, an extraordinary operation. The base hosted, at various points during the war, every major American combat aircraft type: B-17s, B-24s, B-25s, P-38s, P-39s, P-40s, P-47s, C-47s, and dozens of experimental and developmental aircraft passed through Ladd's hangars and hardstands to be tested in temperatures that regularly dropped to 50 below zero. The first winter of operations, the detachment discovered the hangars at Ladd were not yet finished. The aircraft would have to be tested outside, exposed to whatever the Alaskan winter could produce. What the detachment learned was painful and detailed. Airplane heaters did not work, wheels would not turn, controls would not budge. Ice covered the insides of cockpit windshields, brakes froze, hydraulic systems gelled. Tires shattered if an aircraft was moved before the rubber had been warmed. Fuel lines clogged with ice from water vapor that had condensed and frozen. And the bearings of every type and in every location on the aircraft simply stopped working. The detachment's reports made their way back to the United States Army Air Force's Materiel Command at Wright Field in Ohio, and from there to the major oil companies and to organizations like the National Bureau of Standards. The reports described in clinical detail exactly what failed and at what temperature. They were a specification document written by hard experience for the chemists and engineers who were trying to solve the problem. The lithium greases that began arriving at Ladd in 1944 were tested under exactly the conditions they would face in operational service. Bearings were packed, aircraft were started cold, propellers were turned by hand, control surfaces were moved through their full ranges, and the results were measured against the baseline of the calcium and sodium-based greases the bearings had previously used. The lithium grease passed tests that no previous lubricant had passed. In the dry, technical language of the post-test reports, the new grease was approved for service use in all aircraft operating in extreme low-temperature conditions. Ladd Field, the same facility that had identified the problem, had now validated the solution. The grease was cleared for general distribution. The proving ground for the new grease was not actually the Aleutian campaign, important as that was. The proving ground was the Alaska-Siberia ferry route, known to the men who flew it as Al-Sib. Between September 1942 and August 1945, approximately 8,000 American military aircraft were delivered from factories in the continental United States to Soviet pilots at Ladd Field for onward flight to the Eastern Front. The route ran from Great Falls, Montana, north through a string of Canadian airfields to Ladd in Fairbanks, where Soviet inspection teams accepted the aircraft and Soviet pilots flew them onward through Nome and across the Bering Strait to Krasnoyarsk in Siberia. The aircraft delivered included Bell P-39 Airacobras, by far the largest category, plus P-63 King Cobras, A-20 Havocs, B-25 Mitchell bombers, C-47 transports, and a variety of trainers and utility aircraft. At its peak, Great Falls was processing 400 fighters, 80 medium bombers, and 15 cargo aircraft per month. Ladd Field expanded from 23 buildings at the start of the program to more than 700 buildings by 1945, housing more than 4,500 American military personnel, plus a Soviet contingent that ranged from 150 to 600 personnel at any given time. The temperatures at Ladd Field regularly dropped to 50 below zero in the deep winter. The aircraft had to fly anyway. The aircraft had to fly precisely because the Soviet Eastern Front, where these aircraft were going, was itself experiencing some of the coldest combat conditions of the entire war. A P-39 Airacobra that could not be started at Fairbanks in February was not going to be useful at Murmansk in February either. The mechanics at Great Falls, at Edmonton, at Whitehorse, at Watson Lake, at Northway, and at Ladd Field all needed lubricants that worked. The grease that they packed into the wheel bearings, the propeller hubs, the magneto bearings, the supercharger drives, and the dozens of other lubrication points on every aircraft they handled had to survive temperatures the original American designers had never anticipated. By 1944, with the lithium-based greases moving into service across the entire Alsib route, the operational readiness numbers at Ladd Field climbed steadily. More aircraft were leaving for Siberia on schedule, fewer were grounded for bearing or lubrication problems. The Soviet acceptance teams, who had previously rejected aircraft for issues that included bearing seizure during pre-flight runs, began accepting nearly every aircraft delivered. The Soviet records on the receiving end, in Krasnoyarsk and the destinations beyond, confirmed the same pattern. The American aircraft arrived in better operational condition than they had in 1942 and 1943. The losses along the route were still significant. 133 aircraft crashed in North America on the Alsib run. More than 100 American pilots and crew died. 44 more were lost over Siberia, with at least 100 Soviet airmen killed between Fairbanks and Krasnoyarsk. The weather was still the greatest single killer, but mechanical failures on the ground, the kind of failures that had crippled the program in its first winter, were no longer the dominant cause of mission abort.
The Aleutian campaign ended officially in August 1943 with the unopposed American landing on Kiska, but the air war in the North Pacific continued to the very end of the conflict. From bases at Adak, at Amchitka, at Shemya, and at the new field constructed on Attu after its recapture, the 11th Air Force conducted long-range bombing missions against the Japanese-held Kuril Islands, the chain that runs south from the Kamchatka Peninsula to the home islands of Japan. These were not short missions. A B-24 Liberator flying from Attu to Paramushiro in the northern Kurils flew approximately 700 miles each way, with most of the flight conducted over open ocean in some of the worst weather on the planet. The aircraft typically cruised at altitudes between 12 and 18,000 feet, where outside air temperatures even in summer fell well below 0 Fahrenheit. In winter, with cold soak times measured in hours, the ambient air around the aircraft at cruise altitude could reach 50 below. The bearings that mattered for these missions were not just on the engines, they were on the turbocharger assemblies, where shaft speeds reached 30,000 revolutions per minute. They were on the supercharger drives, which transferred power from the engine through gearboxes that ran at extreme temperatures, while their housings were cold-soaked at extreme low temperatures. They were on the propeller pitch change mechanisms, the actuators that adjusted the blade angle of the propellers from cruise to climb to combat power and back again. Every one of these bearings depended on grease. The performance of those bearings on long-range 11th Air Force missions to the Kurils during the winters of 1943-44 and 1944-45 was a quiet achievement of the new lubricant chemistry. Aircraft that flew 9, 10, and 11-hour missions in conditions where every external surface accumulated frost and the engine nacelle temperatures swung from ambient cold to combat power heat and back, returned to base with their bearings intact. The pitch mechanisms still worked, the turbochargers still spooled, the wheel bearings still rotated on landing. The combat losses from these missions came from Japanese fighters, from anti-aircraft fire, from navigational errors over featureless ocean, and from the merciless Aleutian weather. They did not come from grease failure. The aircraft that did not return generally did not return for reasons that had nothing to do with the small, unsung work of Clarence Earl's lithium soaps.
The contrast with the Axis powers on the question of bearing grease was as stark as the contrast on aviation oil. Germany, which had pioneered synthetic petroleum chemistry under Hermann Zorn and his IG Farben colleagues, had also done significant work on synthetic grease formulations. The Germans understood the cold weather problem.
The Eastern Front, where German aircraft operated in conditions every bit as severe as the Aleutians or the ALISB route, had taught them the same lessons American mechanics learned at Lad Field. The German solution was a combination of synthetic base oils, primarily diester chemistry, combined with various non-soap thickener systems that they had developed through the IG Farben research program. The greases worked. In some respects, particularly at extreme high temperatures, they were superior to the lithium greases the Americans were producing. But like everything else in the German wartime industrial economy, they were expensive to produce, slow to manufacture, and dependent on synthetic chemistry infrastructure that was vulnerable to bombing. By 1944, the same Allied bombing campaign that was destroying German synthetic fuel and synthetic rubber production was also destroying the supporting infrastructure for synthetic lubricants. The chemical plants at Luna, at Ludwigshafen, at Hulls, and at a half-dozen other sites that produced the precursors for German lubricating greases were hit repeatedly. Production fell. Distribution networks were broken by the destruction of the German rail system. Forward Luftwaffe airfields by late 1944 were operating on whatever grease they could salvage, mix, or improvise. The Japanese situation was worse. Japan had no significant domestic petroleum industry, no synthetic chemistry infrastructure of any consequence, and increasingly little access to the lubricants that had been imported before the war. The bearings on Japanese aircraft operating in the North Pacific Theater, including the long-range Mitsubishi G4M bombers and the Mitsubishi A6M fighters defending the Kurils, were lubricated with whatever was available. By 1944, that often meant reused grease, mixed grease of uncertain composition, or grease that had been substituted with the closest available alternative when the original specification product was no longer obtainable. American captured equipment reports from late 1944 and 1945 describe Japanese aircraft with bearings that showed signs of inadequate lubrication, of contamination, and of operation outside the design temperature range of the lubricants installed. The aircraft still flew when their pilots could find fuel. They flew less reliably, with more maintenance, with shorter service lives than the American equivalents. The lithium grease that the Americans had developed and deployed was, like the Pennsylvania-grade aviation oil that lubricated the bomber engines, a quiet industrial advantage. It did not show up in the gun camera footage. It did not appear in the operational summaries. It simply meant that mission after mission, the American aircraft were ready to fly.
The lithium grease did not apply itself. The aircraft did not maintain themselves. The mechanics who serviced the bombers and fighters operating from Arctic and Pacific bases in 1944 and 1945 were the men who actually closed the gap between Clarence Earl's chemistry patent and the operational reality of a B-24 Liberator launching from Attu at 4 o'clock in the morning to bomb Paramushiro. The mechanic in Arctic and subarctic service learned a particular set of skills that did not appear in any manual. He learned how to keep his hands functional in temperatures that frostbit exposed skin in less than 2 minutes. He learned to work in moose-hide mittens until the moment a task required fingers, at which point he removed the mittens, did the task in as few seconds as possible, and replaced them before the cold could damage his hands. He learned to drape canvas tarps over engine nacelles and run propane salamander heaters underneath to warm the entire engine assembly before any work could begin. He learned to keep tools indoors until the moment of use because a steel wrench at -40 would freeze instantly to any exposed skin and tear it off when removed. He also learned the new grease. The training was informal. A non-commissioned officer who had been at Lad Field longer than the newcomer would show him how to repack a wheel bearing with the new lithium grease, would explain that the new grease did not need to be heated before application the way the old calcium grease did, would point out the changes in procedure that the new lubricant allowed. The cumulative effect of thousands of mechanics learning the new procedures, applying the new grease according to the new specifications, and bringing aircraft back to operational status faster than they had been able to do it in 1942 was measurable in mission completion rates. The 11th Air Force by the winter of 1944-45 was running operational tempo numbers that would have been considered impossible 2 years earlier.
The men who did this work were not famous. Most of them have no biographies. The aircraft they serviced are mostly gone, scrapped after the war, or lost in accidents during their service lives. What remains is the institutional fact that the United States Army Air Forces, in the most severe operational climate of the entire war, achieved aircraft availability rates that the Luftwaffe and the Japanese Army Air Force never matched. The grease they used, the small steel cans of yellow-amber semi-solid lubricant stenciled with the wartime military specification number, was a part of how that happened. Not the only part, not even the most visible part, but a part that, without which, none of the rest of the system would have functioned. When the war ended in August 1945, the wartime production lines that had manufactured millions of pounds of lithium-based aircraft grease did not stop. They redirected. The same chemistry that had kept American bombers flying in the Aleutians and along the Alaska-Siberia route turned out to be, in peacetime industrial use, the most flexible and reliable lubricant ever developed for everything from automobile chassis lubrication to industrial machinery to household appliances. By the late 1940s, lithium-based greases had displaced calcium and sodium soap greases across nearly every application in the American economy where grease was used. The automobile industry adopted lithium grease as the standard for chassis lubrication, where it remained dominant for the next 30 years. The aerospace industry, including the new commercial airline business that emerged in the late 1940s and 1950s with aircraft like the Douglas DC-6, the Lockheed Constellation, and the Boeing Stratocruiser, used lithium grease for nearly every airframe lubrication application. Industrial bearings, agricultural equipment, construction machinery, marine applications, and eventually consumer products from electric motors to garage door tracks all converged on the lithium soap chemistry that Clarence Earl had patented in 1942. The lithium complex greases that followed, developed by Lester W. McLennan in 1947 under United States Patent number 2,417,428, extended the operating temperature range further still by adding a second thickener component, typically a short-chain difunctional carboxylic acid like azelaic or adipic acid. Lithium complex greases did not gain market dominance until the 1980s, but when they did, they replaced simple lithium greases as the industry standard. Today, more than 70% of all grease sold worldwide is based on either simple lithium soap or lithium complex thickener. The chemistry that allowed an American B-24 to start in February at -48°F at Ladd Field, Fairbanks, Alaska in 1944 is the same chemistry that lubricates the wheel bearings of the car parked in front of your house today. The military specification numbers have changed, the performance requirements have been tightened, the base oils have evolved from straight mineral oils to synthetic hydrocarbons, but the lithium soap thickener, the structural innovation that Clarence Earl described in his 1942 patent, is still there. This is the silent inheritance of the wartime cold weather lubricant program. The men who developed it, the chemists at the major oil companies who scaled it to production, the mechanics who applied it on freezing hardstands at Aleutian airfields, and the pilots whose engines started reliably because of it, all of them contributed to a chemistry that has outlived them. The grease did its job. It is still doing its job.
There is a calculation that nobody at the time bothered to write down, but that is implicit in every operational report from the 11th Air Force during the winters of 1944 and 1945. The calculation is this: an aircraft that cannot start cannot fly a mission. A mission that does not fly cannot drop bombs. Bombs that are not dropped do not destroy targets. Targets that are not destroyed continue to support the enemy war effort. The chain of causation is direct, and it terminates not at the pilot, not at the engine, not at the propeller, but at the grease packed into the bearings of the engine accessories and the propeller hub mechanism. The grease was the bottleneck.
The lithium chemistry developed by Clarence Earl and produced in industrial quantities by the major American oil companies starting in 1943 was what removed that bottleneck. The 11th Air Force flew approximately 1,500 sorties against the Kuril Islands between July 1943 and August 1945. It delivered approximately 3,500 tons of bombs on Japanese targets in the northern home islands. It tied down a Japanese Northern Area Fleet defense establishment that, had it been deployed elsewhere, might have changed outcomes in the Central Pacific or in the air defense of the Japanese mainland. The campaign was, by the standards of the 8th Air Force in Europe or the 20th Air Force in the Marianas, a minor effort. But it was conducted in the worst flying conditions of the entire war, with aircraft that had not been designed for those conditions, and it succeeded. The ALISB ferry route delivered approximately 8,000 combat aircraft to the Soviet Union. Those aircraft, including the P-39 Airacobras that became the mounts of Soviet aces like Alexander Pokrishkin and Nikolai Gulayev, flew combat missions on the Eastern Front in temperatures that matched or exceeded anything the Aleutians could produce. They flew because the bearings on those aircraft, lubricated with lithium grease developed and manufactured during the war, would still rotate at -40. The men who did this work are mostly gone now. Clarence Earl, the chemical engineer whose 1942 patent quietly transformed lubricant technology, has no monument. Colonel Dale Gaffney, the cold weather test detachment commander at Ladd Field, who validated the chemistry under operational conditions, is a footnote in Alaskan aviation history. The mechanics, the Sergeant Andersons who spent their winters frostbitten at Ladd and Adak and Shemya, are nearly all gone too. The B-24s and B-17s they serviced are scrapped or sit in museums. What they left behind, like the Pennsylvania-grade aviation oil that lubricated the engines they maintained, is a quiet legacy, a chemistry, a specification number that survived the war and became the basis of the lithium grease industry that today, 84 years after Earl filed his patent, still serves every kind of machinery built anywhere on Earth. War decides what flies. It also decides what chemistry survives the war and shapes the industrial economy that follows. The lithium grease developed for Arctic bomber missions did both. The bombers got home, the chemistry stayed. If this kind of unsung industrial detail interests you, the chemistry that quietly decided campaigns nobody famous remembers, the chemists and mechanics whose names never made it into the popular histories, like the video and subscribe. The men who packed the bearings of the bombers that flew the Aleutians and the ALISB route, who developed and produced the lithium grease that kept those bearings turning at 50 below zero, deserve to be remembered too. They flew the war they were given, in conditions the designers never planned for, with chemistry that had not existed 5 years earlier. That they made it work at all is one of the quieter miracles of the Second World War.